All right. So we're going to start off with a couple examples, and they're more of this kind of problem, which I've realized as well. So this book is a new book that we're using, so it's the same content, it's just kind of rearranged. I didn't realize. So these kind of problems, they're called composite area problems. Um, if you're following around the textbook, properly speaking, these are in 1.6. They have a whole kind of section about different shapes that are put together, and you find the area by kind of breaking them apart, computing the smaller area pieces, and then adding them together. But we're just kind of doing it along the way. So we'll do more at the end too when I technically cover 1.6. But note that as well. So we follow the book, but not to the letter. All right. So let's do some examples. So find the area of the grass, and so I put like some dashes to denote where the grass was. It's this kind of outside area. All right. This inside area, I don't know. Maybe it's like a concrete pad or something. Maybe there's a water feature in the middle, right? You can make up your mind. It's a parallelogram, right? The whole garden's a parallelogram. I have this rectangular fountain in the middle, and then there's grass around it. All right. So I want to find the area of the grass. What can I do? So we know the area of a parallelogram, right? And we know the area of a rectangle. So the area of a parallelogram is just base times its height, right? And remember we did that. I'm not going to go through it again, but remember we did that. We kind of chopped off the end triangle, and we took it and we moved it to the right-hand side. And it turned out that the area of that resulting rectangle, was exactly the height, which is that vertical stripe here, times the base, which is down here. Right? So we can compute the area of the whole parallelogram. And then what we can do is we can compute the area of this rectangular bit, right? Because we can also compute areas of rectangles pretty easily. And then we can just subtract the two. I just want the area of the grassy bit. So I'm going to take the whole area of the parallelogram and subtract off the area of the rectangle. There you go. So I didn't really give myself any room. So maybe I'll do it off to the side here on another sheet of paper. So let's see. So the area, there we go. Parallelogram. Right, so we'll compute that first. And so we go back to our little diagram. And we note that the height is 60 and the base is 90. So it's just 60 times 90. Now, if you're looking, you'll be like, might be like, why do I give you, what is this 80 for? And any ideas? What if we can use this 80 for anything?
Is it width?
It's kind of nothing. You could think of it like a width. Like if this is your length, this could kind of be your width. But it's like superfluous information. So I gave you this just to kind of try to throw you off. So always be careful. Make sure you're taking the right measure. So if this is 60, so like if I draw a line here, right, this is 60 feet properly, but that's going to be the height that we talked about last time. So the height is always the literal how high is your parallelogram, not necessarily how long is the side, right? Now the base is going to be that, but yeah, there we go. All right. Anyway, as I was saying, so this would be 60, the height times the base, 90. So base times height. So the base I said was 90 feet. And what did I say the height was? 60. And now we just use our handy dandy calculator. There we go. So 90 times 60 is 5,400. And we talked about this last time, right? The units for the area are just going to be squared. So when I compute 90 feet times 60 feet, I obviously multiply the 90 and the 60, and that's what we just did on our calculator. But I also multiply the units, so it's feet times feet. So it's feet squared. Right? So always remember your units for area are a little different than what you might expect. All right, so that's the area of the parallelogram. Now, as I said, we need to compute the area of the rectangle inside, which has no grass. So area of rectangle. And the area of the rectangle, oddly enough, is just base times height as well, recalling from last class. You can also think of it as length times width if you're more familiar with that notation. Same thing. And so here, my base is going to be 55. It's going to be this length. And my height is going to be just the height of your rectangle, 20. So it's 55 times 20. 55 feet times 20 feet. And again, I plug that in my calculator. So I get 1,100 feet squared. Again, feet squared because while you're multiplying the 55 and the 20, you're also multiplying the feet by the feet. So everything's multiplied, all right? And now I just subtract the two. So I get 5,400 minus 1,100. So 4,300. Oh, you can't see that. 4,300 feet squared. So that's the area of the grassy bit. Grassy area. Area of grassy area. I don't know. Maybe I'll put grassy bit. You can phrase it however you want. Right? Does that make sense though? So again, we wanted to compute the area of just this outer kind of rim, not the area of the little fountain. So we just subtract off the area of the fountain from the hole, and we have exactly the area of the grassy bit. Right? Any questions with that? All right, so it's kind of a neat technique. All right, so let me get rid of that. Let's do another one. So we'll do two. This one's a little different. Hopefully you can see that. It's just a little, and we try to, it's not tragically important what the numbers are. But basically, the premise here is that we have 1, 2, 3 triangles, and they're all kind of stuck together. So what can we do to find the area of this whole triangular region? Like I want this entire area. How am I going to find it? In the previous one, right, we found the area of the bigger section, we subtracted off the area of the little section. This time, we just have 3 kind of independent triangles that we want to find the total area of. So how can we find the total area? Anyone? It's a quiet day. Thursdays
Do
are
it 3 separate times and then add them all together.
Thank you.
I keep saying it, but then I realize my sound is off.
That's okay. Yeah, so we're just going to add them together, like she said. Just consider them to be separate, kind of like the example we did on Tuesday, except this one's already broken into pieces for us. So remember, the area of a triangle is just 1/2 base times height. So area of triangle is 1/2 base times height. I'm going to move this out now. There we go. All right, it's too close to my hand. I was camping last weekend, and boiling water while camping is tricky, and I dumped it on my thumb, hence the Band-Aid. So I apologize for the slight grotesqueness. But so we're just going to do all 3, like I said. Again, ignoring my thumb. So I'll call this one A1. I'll call this area A2, and I'll call this area A3. And so whenever you're doing these kind of problems and you're doing different sections, feel free to label things. It's always good to label. So the area of A1, and I'll do them independently. So remember, it's just base, 1/2 base times height. I already give you the base and the heights for each, right? The height is literally how high the triangle is. The base is the base. So you can usually, well, always, the height and the base are kind of going to be perpendicular. So like your height will be like that, like something like that, and your base will be with the bottom that your height kind of comes out of, if there's ever any confusion. So it's just 1/2 8 times 12. So what is that, 48? Because 8 times a half is 4, times 12 is 48. Oh, and I give you all, they're all in inches. So it's going to be inches squared. Okay. Let's do area 2. Again, the same formula, but I kind of twisted it a little, right? And so now my height here is, it's 4 inches, if you can't see that. And then the base, oh no, I'm sorry, I didn't read myself. The height's 7 inches and the base is 9 inches. So it's gonna be 1/2 times the base, which I said was 9, times the height, which is 7. What is that? There's not, it's gonna be an ugly number, right? So maybe I'll just plug in my calculator. So 9 times 7 divided by 2. 31.5 inches squared. Okay. Again, inches squared because everything is in inches. Okay. And the last one, area 3, same formula, 1/2 base times height. Here, again, it might be a little difficult to read because I use pencil, but the base is this distance and I put 4 inches and the height is that height and it's 5 inches. So it's going to be 1/2 the base, which I said was 4, times the height, which I said was 5. So this one's easier to compute, right? 1/2 times 4 is 2, so it's 10. And now we just add them all up. All right, so what do I get? 58 plus 31.5. I guess I can do it all straight. So 48 plus 31.5 plus 10. 98 or 89.5. And again, it's all inches squared. Right. And so that's the total area. Right. So just a couple different kinds of area problems. I think I got a couple more at the end of class that involve circles. So we'll practice a little more with these, but it just is a nicer application to kind of use these area formulas, because otherwise it's just kind of the same thing over and over again. All right. And the other thing we did, I think we ended with this on Tuesday, was the Pythagorean theorem. So in this lot of questions, I'm asking you to find the missing leg of the triangles. And you'll note that, well, you will note, they're all right triangles. Right triangle. So remember, a right triangle is just a triangle that has a 90-degree angle in it, right? That is to say that 2 legs of the triangle meet perpendicularly. So like a corner of your room, the walls meet, hopefully, perpendicular, so they're 90 degrees to each other. That's all it means. And a triangle, if you recall, is 180 degrees in it. We don't really do degrees, but it has 180 degrees. And so if one corner is 90, then the other 2 have to be smaller, right? And so the side opposite the 90 we call the hypotenuse, the longest side. And so in the Pythagorean theorem, so I guess I'll put it up here just to reference. Pythagorean theorem. All right, so in the Pythagorean theorem, I have a squared plus b squared equals c squared, where c is the hypotenuse, or longest side. All right. So you don't need to know the definition of hypotenuse except outside of the fact that it's the longest side. And these are the smaller sides. For the A and B, the order doesn't matter, right? Because addition is commutative, so you can flip them and doesn't change anything. But the C has to be the longest, otherwise the formula won't work. All right. Anyway, so now that we kind of got that off to the side, let's look at this triangle, right? So I have 6 and 9, and then this side is the missing side, right? Missing side. So just based on the picture, you can kind of tell or even guess that the missing side is the longest side, right? And the other way you would know that is that it's opposite the 90 degrees. So this little box, that little box means 90 degrees. So whatever side is across the triangle from the 90 degrees or opposite it is the hypotenuse. So this is my C, right? And so now once we've identified all the sides, right, we've noted that this is the biggest, so that's C. These are the smallest two, so it doesn't matter, they're A and B. We can plug it all into the formula and solve for the missing variable. So as I said, C is missing. So I plug in, I'll just do 6 equals A and 9 equals B. Oops, 9 equals C squared. Right. And most of these, you'll need a calculator to compute C or A or B for that matter, just because square roots are often non-trivial. So let's give this a go. Okay, there we go. So I'll compute 6 squared and 9 squared. So 6 squared plus 9 squared is 117. So that tells me that 117 equals C squared. And now I just need to take a square root to solve for C. And so yeah, make sure you take a square root and that you don't divide by 2 or anything. The 2 is in the exponent, right? I'm not multiplying C by 2. This notation means that 117 equals C times itself. So C times C equals 117. So if I divide it by 2, I'm not doing anything really to solve for C. I need to take a root, a square root. And again, in your calculator, like on this one here, it's just above the x squared. So it's down here on the left, lower left. So you'll do second square root button and then 117. And you get, as you see, you'll get some number. As I said, they're more often than not going to be pretty. There's a handful of triangles that have nice sides, like integer sides, but more often than not, they're going to be ugly. So just round to 1 or 2 decimals. So here C equals, I don't know, 10.82. And I didn't give you units in this triangle, right? I just said it was 6 and 9. So there's no units, so I'll just leave it like that. All right. Any questions with that one? Awesome. Let's try another one. So this is my missing side. Right? And now we want to see where the hypotenuse is to see if that's our missing side or if our missing side is just one of the smaller
Excuse me,
ones.
Matt.
Yeah.
Sorry, can you go over that one more time on how to do it in your calculator? Because mine didn't come out like that in my calculator.
Oh, sure.
Will you do the square root?
Do you have one of the scientific or graphing?
It's scientific.
All right. So this is the one I have. It might be similar to yours, hopefully. Oops. Why is there a syntax error? Hold up. There we go. All right. All right. So on this one, so you should have you probably have an x squared button. And so what you'll do is you'll press the second button, because if you look above this x squared button, it's like a little square root symbol up there.
Yep.
You can kind of just see it. So you press second, x squared, and then put in 117. And
okay.
yeah.
I put the number in first.
Oh,
okay.
yeah. Yep.
Gotcha.
Hopefully that works. Yeah, some calculators you do that. You put the number in first and then you do it. But on this one, and yours probably too, when you press the square root, it'll have these parentheses. And so that means that it's the function, the square root function, and then you're evaluating it at some number that you have to put in afterwards. Yeah.
Okay. Thank you.
No problem. All right. Let's see. So let's try this one. So as I said, we want to identify what your A, B, and C is. Again, A and B don't matter as much to the order, but the C is the important one. So again, you look for the right angle. Here, it's more often than not denoted by a little box in the corner of your triangle. So my 90 degrees is there. And so I go across the triangle and see that this is my hypotenuse. It also might be clear because it's the longest side, although in this graphic, it's not super clear because I just sketched it. So this is my C. Right? Because again, it's across the 90 degrees. And then it doesn't matter which is A and B. I'll take this to be A, and I'll take this to be B. All right? And then you just plug everything into the theorem. So A squared is 7. B is unknown, so I leave it as B. And then equals C squared, which is 10 squared. All right. And now, again, you can plug everything in, right? So 7 squared is 49. B squared is unknown, and 100 squared is, or 10 squared is 100. Right, and now this is just an equation you need to solve. So just like any other equation, you want to get everything. Well, equations are tricky. So in this kind of situation, though, you have basically two kind of things, right? You've got numbers, you got 149, and then you have a b squared. And so basically, the goal is to get everything with a b in it to one side, and everything without a b to the other side. So I'm going to take this 49 and bring it to the right-hand side. And you just subtract 49 from both sides to do that. So I get b squared equals 100 minus 49. All right, so again, just subtract 49 from both sides. And then that's 51, right? You can always plug it in your calculator. All right, so I get b squared equals 51. And now we just use our calculator to compute the root again, because it's not going to be terribly pretty. So it's going to be second square root 51. So it's 7.14. So b equals 7.14. Right? And we're rounding. If you want to be really precise, when you round, you can put like a little squiggle. Like you could do b is approximately 7.14. Right. I'm not going to take off points if you put equal to 7.14, because strictly speaking, it's not equal to 7.14. We rounded, but it's close enough. All right. Oh, and this one, I give you units, right? My units are given as centimeters, so it's 10 centimeters and 7 centimeters. So my answer will also be in centimeters. And it will just be flat centimeters, right? We're not doing area here. We're doing length. We're looking for the length of each leg. So it's just straight, just normal everyday centimeters. All right, and the last one. So this one, I don't know, it might be a little repetitive. It's very similar to the previous one, but I kind of swapped the sides that we're missing. In any case, we first need to identify what our C is. So we go to our 90 degrees and look at the opposite side. So 1 inch is my C. And then as I said, B and A don't really matter. So I'll be consistent though, and I'll say A is my missing side. Oops, I can't spell missing, put it in there. Missing side, and we'll say that's equal to A. Sorry about that. And then we'll say B is the 0.2 inches. And now, again, just like the last couple examples, so A squared plus B squared equals C squared, where C is my hypotenuse. So A is missing. So actually, let me just put like a little line there so I don't get confused. So A squared plus B squared is 0.2 equals 1 squared, which is my C. Right? And now we just solve like before, right? So 1 squared is 1, right? Because anything times 1 is 1. So, or anything times 1 is itself. So 1 times 1 is itself, which is 1. So, and the 0.2 we can compute. So 0.2 squared is 0.04. So I get A squared equals 0.04. Oops, wow, plus 1 equals, sorry about that. Put it down here. So A squared plus 0.04 equals 1. Just simplifying it a little. And now just like when we do with B, I want to get everything with that's a number on one side and everything that is an A, in this case, just A squared on the other. So I'll bring over the 0.04 on to the right there by subtracting it from both sides. So I get A squared equals 1 minus 0.04. And then again, we just plop that in our calculator. So let's see here. 1 minus 0.04, and you get 0.96. Oh, you can't see that? There you go. So it's 0.96. And so A squared equals 0.96, and you just do a square root again. So second square root, 0.96. So it's I don't know, 0.98. So A equals 0.98, and this is inches. Sorry, it's a little crumpled. I didn't give myself enough room. All right. Any questions? Awesome. So just a little algebra to find these. But the only thing that you could really mess up on is identifying the hypotenuse. Make sure that's the right one. But other than that, you should be fine. Right. So let's do some word problems involving triangles. Always a good time. Wait, there it is. All right. So a 10-foot long ladder leans against a wall. If the bottom of the ladder is 5 feet from the base of the wall, how high does the ladder extend up the wall? And if you ever take like a calculus course, this is like, I think is it Calc 2? Maybe it's Calc 2. This is like a problem that you'll always see, it's not this exact problem, but it's the same setup. It's you have a ladder leaning against a wall and you have to compute something about this ladder. In the calculus case, the ladder is sliding down the wall. So you have to compute like rate of change and stuff. But for us, we're just talking about a ladder that's just not moving against a wall. And so if you're confused, what I'm talking about is it looks like this. So my ladder's like, I don't know. I don't know how to draw a ladder from the side. There's my ladder. Right? This is the wall. And this is the floor. Right? So it's 10 feet long, the ladder, and it leans against the wall. And the bottom of the ladder here is 5 feet from the base of the wall here. So this is 5 feet. How high does the ladder extend up the wall? So I'm asking you to find this distance. And again, hopefully your house is constructed sufficiently well so that your walls on your floors meet at a 90-degree angle. I know that's not true for all houses. I've seen several houses looking at houses that floor is horribly crooked. I don't understand how these things happen, but they do. It's probably just old houses. Anyway, we'll assume all of our houses are 90 degrees. So essentially the idea is it's just a right triangle, right? The two legs are the wall and the floor. The ladder is the hypotenuse because it's across from the 90 degrees. We know two of the sides. We know the hypotenuse is 10. We know the floor is 5. And we want to find how high it is on the wall. So I'll just label these things. So I'll call this C, I'll call this B, and I'll call this A. And so now I just use the Pythagorean theorem. So I get A squared, again, A is unknown, plus B squared, B is 5, so 5 squared, equals C squared, 10 squared, 100. And now, just like the past couple problems, we just solve for the missing side, A. So, so what do I get? I get A squared plus 25 equals 100. Again, I want to get the A squared by itself, so I can take a square root. And so I get A squared equals 100 minus 25. And so that's 75. So A squared equals 75. And so I don't know, I haven't showed you. I should note, so when you take a radical, what you're really doing is you're taking a square root of both sides, right? I don't know if that's clear. So what we're doing is we're saying that, oh, if A squared equals 75, then the square root of A squared equals the square root of 75. But the square root and the square cancel. They're inverses of each other. Again, inverse functions are something you'll do if you take like pre-calc as well, but they're inverses, so they cancel. It's like if you take a number and add 1 and then subtract 1, you'll always end back where you started with. So it's the same idea. In any case, it's just A. So A equals the square root of 75, right? And I'm in feet, so that's feet. And more often than not, people want a nice answer. So you can compute exactly what the square root of 75 is, or at least close to what it is. And so it's about 8.66 feet. Right? And there you go. So if the base of the ladder is 5 feet away from the wall and the ladder's 10 feet tall, then you know that it's 8.66 feet up the wall, which is kind of cool. But any questions with that? Again, so just some algebra. Hopefully the more you do some of this algebra, the easier it gets for you, especially if you're struggling with algebra. But yeah, let's do another one. So this one involves a sailboat. So we have a large sail in the shape of a right triangle. The longest edge of the sail, so the longest edge, what does that mean? The hypotenuse, right? So kind of make sure you're taking out parts, so the longest edge, hypotenuse. 17 yards, and the bottom edge of the sail is 8 yards. How tall is the sail? Right. So, the only difference with these word problems and the problems we just did are that the triangle is not drawn. It's sort of hidden in words. So the only tricky part might be kind of figuring out what the triangle is based on the words. But you know, a lot of times like here, you'll longest edge, hypotenuse, and then the bottom edge is just one of the legs. So what it's saying is that it looks like this. So it's a right triangle. The longest edge is 17 yards. So that's the longest side. And again, it's gonna be opposite the 90 degrees in your triangle. And then the base, or the bottom edge of the sail, is 8. So down here is 8 yards. Right? So presumably my sailboat looks something like this. Right? I don't know, maybe it has some windows. There we go. So that's my sailboat. And it wants how high it is. Right. So again, everything's kind of laid out. We just got to compute it. So again, my hypotenuse is 17. Call that C. My bottom here, I'll say is B, and I'll keep this as A, again, just to be consistent. And then you just use the Pythagorean theorem. So A squared plus B squared equals C squared. So A squared is unknown, B is 8, and then 17 squared is the C. So same kind of thing. So A squared plus 64, and then I don't know what 17 squared is. What is it, 149? No. 289, I was really off. 289. Hey. And now we just solve. So just like in all the 5 examples we just did, 4, I'll bring over the 64. So I get A squared, 289 minus 64. Right? And again, you can use your handy dandy calculator. So 225, oh, you can't see that, 225. So A squared is 225. And then you just take a square root of both sides. So A equals the square root of 225. Right? And you could, as I said in the previous problem, you could leave it right there. So the square root of 225 is an exact answer. But you could also get an approximation. So second square root, 225 is 15. So that's a really nice one. So A equals 15 feet. It's exactly 15. So yeah, some triangles will have.
How did your yards go to feet?
Because I like feet more apparently. Thank you. Sorry about that. And everything else look good? I think so. All right. So yeah, so I was saying some triangles have nice integer sides. So they have like nice number or natural number sides. Most don't. So just be aware of that. All right. Any questions with triangles? No? All right. So let's move on. So we've done triangles, rectangles, parallelograms, trapezoids, all this stuff. Let's move on to something less liney. Let's talk about circles. So it's very dark today. Sorry about that. I have the same lights on. It just seems dark. But let's talk about circles. So a circle is a set of points which are a fixed distance away from a fixed point. It sounds kind of repetitive, but all that means is, so like say you put a piece of point right there, right? And I should have got some string, but if you take a pencil and a pen and you put a string and you tie them together and say you put the pen down on a sheet of paper, right? So fix the pen and there's a string tied to them, right? So just fix the pen and then you rotate the pencil around the pen. You'll get a circle with radius, whatever length the rope is. And so that's all this means. It's a set of points which are fixed distance away from a fixed point. It's just 2 pens tied together with a rope. The rope's length is the radius. Whatever pen you fix is your center. And you get a circle if you rotate the pen around the other pen, or pencil around the other pen. Right? Anyway, we call this distance the radius. The two radii distant line segment across the middle of the circle is called the diameter. And that's a confusing definition, but again, let me draw it. I'll use pencil because I can't not make a mistake. All circles are approximations. It's a really bad circle, but forgive me. So this is my center. And then I have a radius, And so the radius is the same on the entire circle. And then if you take two radii, and you put them next to each other, you'll get a line segment across the center of the circle. So if I put a line segment like here, this is my diameter, which is 2 times the radius. All right. So again, I think a lot of people have already seen these kind of things. So hopefully radius, circumference, or diameter, you hopefully have seen before, but feel free to ask questions if something's confusing. The distance around a circle is called the circumference. Okay. So their circumference is basically just the perimeter of the circle. It's the length around your circle. If you take a piece of string, I have string. I should have cut some off. I didn't even think about that. I'm sorry. If you have a piece of string at home, draw a circle, and then to measure the circumference, you can just put the string around the circle and then straighten it out against a ruler and then measure how long the string is, and that will be the circumference of whatever your circle is. Right? So there's all these fun games you can do with circles. But what's really interesting is that for every circle, this ratio of the circumference to the diameter is exactly the same. We call it pi, right? So the ratio to circumference to the diameter is just circumference over diameter. All right. So you take, again, whatever your circle is, and you can do this at home. Draw a circle with a string and 2 pencils, and then using another piece of string, measure what your circumference is, what the perimeter, how around your circle is. So just take the string, as I said, lay it around it and then measure it. And then divide that by the diameter, and you'll get something close to 3.14, which is pi. And there's more. I don't know the digits of pi. There's crazy people who know like billions. But on your calculator, like on mine, it's above the exponential button. It's this little pi. So you'll do second pi, and then I think it's the same on these, maybe not. On the scientific ones, it's somewhere. Where is it? I don't see it right away. It doesn't matter. I don't, try to find on your calculator. I don't see it in the scientific one I have, but I'm assuming it's there somewhere. You can always just use 3.14 for our purposes. The only reason you use more digits is if you're doing something like related to engineering or like industry, or you're doing something scientific where you need a lot of precision. Basically, the thing with pi is that it's a non-repeating decimal. So even if you put 1,000,000 digits, you'd still be approximating, and you would still not find a pattern. There's no pattern. Like, it would never repeat, regardless of how many digits you put there. And so usually you just round it. But as I said, you can do as many as you like. On the homework, I'm not sure what my Open Math will accept. I'm assuming just do as many as you can for my Open Math, but as far as like tests and projects go, it doesn't matter to me how much you round pi. Just know that it's non-repeating, it goes on forever, but it's about 3.14. All right. Anyway, as I was saying, so the important thing about pi, though, is if we know the diameter and we know what pi is, we can then compute their circumference by just multiplying them. Right? So what I said here is the ratio of the circumference to the diameter is pi. So what I was saying is that if c is the circumference and d is the diameter, then pi equals c over d. And so if I multiply d on both sides, I get c equals pi times d. Or pi times the diameter. And the diameter, we said, was 2r. So I can also consider this to be I'll write it like pi times 2r, the radius. Right? So alternatively, this is pi d and 2 pi r. Right? Usually, if you're looking up if you're looking up formulas online, I think it's almost universal. You'll see pi d and 2 pi r. No one writes it as like radius and diameter so much. Yep. So any questions so far? This is actually really interesting, this pi business. And it's a neat, if you're really bored, it's a cool project. And all you need is 2 pencils and a piece of string. You could pretend you're like an ancient Greek person. That's like what they did. It's amazing what you can do with like a compass and a piece of string and some pencils. Amazing. They asked questions that weren't answered until like 18th century or even more recently. But anyway, so we have some formulas for circumference. Let's try to use them. There we go. So find the circumference of a circle with radius of 5 feet. So as I said, circumference was equal to 2 times pi times radius. So you just plug it in. So it's 2 pi times 5. And it's going to be feet. Right, so you could write this as 10 pi feet. Right? Or you could plug it in your calculator. So if you don't have a pi button, you could just do 10 times 3.14, and you get 31.4. Or if you do have a pi button, so I'll do second, where'd it go? Pi times 10, you get 31.41. So it's about 31.42 feet. I usually round to 2 decimal places. But either of these are acceptable answers. Again, if you do take like a pre-calc or like a calc course, more often than not, you'll encounter your instructor will tell you to leave the pi. People usually like this answer more than this answer because this is exact. It's exactly 10 pi. Whereas the second one where we plugged it in our calculator is an approximation, hence the squiggles. And so it's a rounding. It doesn't matter for us because nothing we're doing is like critical. But if you are doing applications, you do want more precision. You'll have to use the exact form. All right, let's try another one. What's the radius and diameter of a circle with circumference 24 millimeters? Right, so this is like going the opposite way, right? In this problem, I'm giving you a circumference, 24 pi millimeters, and I want the radius and diameter. So just remember the formula. So circumference is pi d, or 2 pi r, where d is diameter, c is circumference, r is radius, and pi is obviously pi. So if I know my circumference is 24 pi, and I'll just drop the units for now, we can put them in at the end. So what is my diameter going to be? So like compare these two, right? If 24 pi equals pi times d, what is d necessarily?
24.
Yep. And again, my units are millimeters, so that's millimeters. And then if 24 pi is 2 pi r, what is r necessarily? Or you can think of it as if the diameter is 24 and the radius is half the diameter, what is my radius?
12.
Yep. All right, so there you go. So from the circumference, you can kind of get the other information too. You can go back and forth pretty easily just by solving some equations. All right. What was I gonna say? Oh, and I just want to make I hope it's clear why. So like here, we're the radius is in feet, so the circumference is in feet, and down here, everything is in millimeters because the circumference is in millimeters.
You can only put 1 m instead of 2.
Oh, thank you. Not meters. And so, I'm telling you, I'm not great with the attention to detail with the units. I never use math people don't use units generally unless they're doing like applied math. So I feel like physics people are really professionals with units. I'm a little sloppy, admittedly. But I was like, oh yeah. So the circumference, as I said, is if you take a rope and put it around the circle, and then you trim it so it's exactly goes around the circle, and then you take that same rope and you stretch it in a straight line against a ruler and you measure it. That's the circumference. So the units for circumference are just whatever the units are normally for like radius. So like there's no squares, there's no cubes. It's just like meters or feet or millimeters, all right? Just because it's a length, it's not an area. So let's make sure you're kind of clear on that. But here we go. All right, so let's try some areas now. So anyone know what the area of a circle is based on the radius?
360.
That is the number of degrees in a circle. So it's kind of, you can kind of think of it like the area. But as far as the area in terms of,
Is it, it just, it just escaped me. 180.
that's half a circle. We're not doing degrees. We're just looking for an expression that gives us the area. So it's going to be pi r squared, if you've seen that before. Right, so if I square the radius, multiply it times pi, that pops me out the area. All right. And so to get this formula is a little more complicated. I don't know if you take calculus, you could do it. I don't know, there must be a simpler way, but I don't know it. But yeah, so the other formulas we can kind of get by observation, but this one not so much. So you just kind of got to take it for what it is. Anyway, let's try to use it in an example. So let's find the diameter, the circumference, and the area of a circle with radius of 3. So again, just remember all the formulas, right? So I want the diameter. The diameter, which I'll write as d, is 2r. Right? It's just twice the radius because it's the line segment that goes right across the circle. So I'll put like, right? So that is my diameter. It's at the widest part, you put a line. So it's 2r. What else? The circumference, we said was pi d, or 2 pi r. So 2 ways you can do that one. And again, the circumference is the length around. So if I put like this little thing like that, that's my c. Right, it's like the length around it. You can pretend it's like a string that you've stretched. And then the area is pi r squared. And what you'll note about the area formula is that if you're thinking of units, I'm squaring the radius. And so the units of the area will be squared because I'm squaring the radius. So it'll be squared whatever the units of the radius are. But at this point, we have all the formulas compiled, so we just plop them in. So my diameter is what here? If my r is 3 inches? 2 times 3?
6.
Yeah, so it's 6 inches. So if my diameter is 6, then my circumference is 6 times pi, or pi times 6, and it's inches as well. And as I said, you could leave it like that once everything's plugged in. Like pi is a number, so pi is not a variable. So when I say everything's plugged in, all of the variables are plugged in because pi is not a variable. It's a number. So, but if you wanted something more explicit, you can also do that. So where is it? Never gonna get it. Here it is. Times 6. So it's, I don't know, 18.85 inches. Okay. And so again, so what that means is that the length around this circle is approximately 18.85 inches. And the last one, the area, pi, the radius was 3, so 3 squared. 3 squared is 9, so that's just pi times 9. And this is inches squared. And again, if you wanted to be super precise, you could leave it like that because theoretically everything's plugged in. But if you wanted a nice decimal approximation, you just plop it in your calculator. So second pi times 9. So that's about, I don't know, 28.27. Inches squared. Right, so we've computed all these kind of descriptions or descriptive things about the circle. Right. Any issues with those? So just some formulas. Um, and the last unit in this geometry section, we'll do some volumes. I don't know if, I think one of the things we'll do is volumes of a sphere. So that's another cool one. Again, another thing, if you go and take calculus, which you should at some point in your life, you can actually compute, like find out where this formula comes from. But it's really neat. I would recommend. All right. And now, as I said at the end here, that's it. That's all we need for circles, by the way. We're just doing some area per circumference, diameter kind of stuff. Some what do you want to say? Like the things you talk about when you talk about circles. We're not going to do much else. Like I said, no degrees, nothing like that. No trig. We're just going to talk about some geometric properties. And now we can use them in a more complex situation, right? So I apparently like examples involving grass. So this one, find the area and perimeter of this grassy area. And so in this situation, we have this, maybe it's a yard. Maybe you're designing your backyard. And maybe for some reason, you have a massive fountain in the backyard of your house. And this is like half of it. Maybe it extends over here, or maybe it's like a half of a sphere fountain. I don't know. It's your fountain. Make me whatever you want. In any case, you've got this fountain, which is not grassy. And you also have a flower bed over here, which is not grassy because it's flowers and you don't want grass in your flowers. And so this area here, this kind of awkward looking area, is our grassy bed. And I forgot that I should note what the total length is. So I didn't give you a width. This is 10, let's say it's 20 feet. There you go. So it's on the whole rectangular backyard is 10 feet by 20 feet. Admittedly, it's not a very big backyard. It's a small yard. So it's 10 feet by 20 feet. Maybe this is a koi pond. I saw a house for sale in Olean that had the world's largest koi pond in it. I don't know why you would need such a large koi pond in Olean, but it was a nice house otherwise. Anyway, 20 by 10 feet, and I want just the grassy area. And I want the perimeter. So by perimeter, let me see if I can find something that's not colored the same color. So by perimeter, I want this length. I want this, and then I want like this, up and around and that. So I want all the edge. I want the length of the edge of the grass. All right. So the first thing, let's do the area first. So we're going to do this problem kind of like we did that first problem we did today, where I had the parallelogram with the rectangular water feature in the middle, and I wanted the grass again. So what we'll do is we'll compute the area of the whole rectangle, because on its own, this is a rectangle, right? It's just a big rectangle. So the area of the rectangle is just base times height, right? And I said that this is 10 feet tall and it's 20 feet across. And so the area is just 10 times 20. And it's feet squared because everything is feet here. All right. So again, you plop it and you surprisingly enough get 200. All right. So the whole kit and caboodle is 200 square feet, which is kind of a small yard. I'm sorry, I should have made it like 400 feet. It doesn't matter. Pretend it's bigger than it is. So next, I want to subtract off things, right? I don't want this flower garden. The flower garden on its own is another rectangle. So I can compute that. So area of flowers. And as I said earlier, label things, right? If you wanted to, you could label these A1, A2, A3, or something like that. I'm just going to call them what they are, like area of big rectangle, or area of rectangle, area of flowers, but you can be as precise as you want. So this is 4 times 6 feet squared. That's just 24 feet squared. You know what numbers I hate multiplying? I hate 8 times 6. I don't like it. I don't like multiplying 8 times 6. It's 48, but I did a teaching thing at a Buffalo charter school once, and it was like with first graders or second graders, and the second grader comes up, it must have been first graders. They were tiny. He came up to me, he's like, what's 4 or 6 times 8? And like, I said 46, and even now, I asked myself why I said 46. It was a bad time in my life, and I just get anxiety over 8 times 6 now. This is not 8 times 6, but it reminded me of 8 times 6. Anyway, and then we just need this half circle, and I will note I'm telling you this is exactly half of a circle. If it wasn't clear, it might not be totally clear, but for our purposes, it's exactly half. So area of fountain. So for the area of the fountain, if it's exactly half of a circle, I can put 1/2, right? And then just multiply it by whatever the area of that whole circle is, and it will give me half of the area. So if the area is pi r squared, and again, I'm kind of telling you, I'm giving you the problem. So the radius here is 2 feet. So r is 2. So r squared is 2 squared. And this is feet squared because everything is in feet. And we're good. So what is this? It's just pi times 2. So I can plug that in my calculator. Times 2. And it's about 6.28 feet squared. All right, cool. And so now, as I said, the 200 square feet is the total area of the rectangle. This is the area of this tiny little flower garden, and this is the area of this circle fountain, which I thought would be bigger, but it's not. Oh, it's because my diagram's off. Sorry, hold on. This should be 5 feet. That's my bad. It should be 5 feet because it's exactly half of the height. So it's 5 feet radius. So this should be 5. That's why it didn't look right. Let's do that again. So it's 1/2. So 0.5 times pi times 25. There we go. That looks better. So it's 39.27 feet squared. All right. That's better. All right, so I just subtract them off because I don't want this area and I don't want that area. So total grass area. So it's going to be 200 minus 24 minus 39.27. And so what is that? That is 200 minus 24 minus 39.27. 136.73 feet squared. Cool. So again, the same technique we used in the initial problem that we did today, right? I started with the whole area and I didn't want some smaller bits, so I subtracted them off. If I had wanted them, I would have just left them and did the whole area. But yeah, there you go. So any questions with the area? Right, the perimeter, let's try the perimeter. So let me do it. I'll start a new sheet over here. Oh, I don't think we'll do that one today. Let's see, perimeter. So for the perimeter, what we're going to do is we have to just go around and add up all of these lengths, right? My dog's barking. So, so this top length is 20 feet. So I'll write that down. And I'll put the feet on at the end, right? And then this whole length is 10. This little bit is 4. So this is what?
6.
Yep. So I'll write that down. So 20 plus 6, right? Next, we're in the flower bed. So this is the same as this. So this is also 6, right? And then this part is also 4. So I'll put 6 and 4. All right, we're getting there. Let's see, so now this length, this whole distance is 20. This part of the flower bud is 6. So what is that part on the bottom? Yeah, 14. So we're just subtracting 6 from 20, right?
Could
So-
you also just do 20 plus 4?
20 plus 4.
Yeah, because the 14 plus
Yeah.
the
Yep.
then
Yeah, you
just
can do
add-
that too. Yeah. Yeah, 14. All right, so thus far we have this. We drop down here, over, down, and over again. So now the only thing left is this half circle. But we know that the distance around a circle is just called the circumference, right? And we know a formula for that. It's pi times d, or pi times 2r. And as I said, this is exactly half the circle. Like you took a circle and you cut it in half. So it's going to be exactly half the circumference of this circle. So when I write it down on my list, it's going to be plus 1/2 times pi. And then d here, the r is 5. So what is d?
10.
Yep. It's just 2 times r. So that's half the circumference. Circumference of a circle. With radius 5. Okay. And now we just add this together, and that's exactly the area in orange, or the length in orange here, the perimeter of our grassy. So for instance, if you wanted to fence in just this orange or grassy area, this is going to be how much fencing you're going to need. So again, these are kind of practical things. Like if you do like any sort of construction or home improvement, or I don't know, things like that, you would need this kind of stuff. So 20 plus, what is this? 12 plus 18 plus, and then 5 times pi. So it's about, and again, it's approximately, because I'm going to round because of pi, 65.71 feet. Right? So it's a real thing. You could use this theoretically in your life if you ever have to make a fence for your house, or I don't know, maybe your dog needs a fence, right? But there you go. Any questions? All right, so today's Thursday. So I will see you Tuesday. If you have any issues tomorrow or over the weekend, shoot me an email. We can Zoom or something. But if not, I will see you Tuesday. Good luck.
Hey, Matt.
Yeah. Oh, there's a
Hello.
chat. Yeah.
Yeah, I was hoping I might be able to Zoom with you again, because I had the idea. I was trying to do the homework, so I was having a little bit